Welcome to another segment of High School Geometry with Netz and Weichel. This is Mrs. Netz,
And this is Mrs. Weichel.
and today we are looking at 7.3 special right triangles. These are our triangles that are special.
They are special.
Oh my lord. What are we doing? Well, by the end of the lesson, you will be able to determine all side lengths in two types of special right triangles. Basically, we have these two triangles that if you understand them and you understand the ratios that represent them, you have a lot less math to do.
Yes.
So, why do you need to know this? Well, number one, it'll save you doing a lot of math you don't need to do. That's number one. But number two, knowing your special right triangles will help you understand the unit circle that will be used in Algebra 2.
Yes, it will.
Then, how will you know it? Well, you will know you've mastered it when you can determine the correct multiplier given a special right triangle.
So today, I would actually like it if you did not have your calculator out.
Put it away.
Put it away. Because if I ask for an answer where you need your calculator, I don't need to show you how to use a calculator for what we're doing today. So with these special right triangles, they are specific types of triangles, whereas what we were doing in 7.1 and 7.2, you had right triangles, but everything else was kind of a variable. You didn't have to be anything specific. Today, you specifically have to have certain kinds of triangles. So for writing your answers, there are times where you're going to be dividing out a square root. So we need to always give an answer in a simplified form, like reducing fractions or simplifying square roots. When you divide by a radical, you cannot leave the radical in the denominator of your answer. That is not a simplified answer.
That's almost like leaving a negative exponent in the denominator. You just don't do it.
Can't do it. So the process for getting rid of it is called rationalizing a denominator. You're going to rationalize it by moving that denominator, the radical, to the numerator from the denominator. Okay, so the process for moving a radical from the denominator of a fraction to the numerator. Fractions are always simplified, and having an irrational denominator is not simplified completely. So that's just reading what you guys have on your paper.
Fill in
That's
your
basically what we
blanks.
were saying. How do you do this?
Easy.
Here's your
Oh my gosh,
steps.
so easy.
So the steps you need to be writing down, you're going to multiply the top and bottom by the denominator. Then you just simply simplify it.
Now, the reason we're multiplying both our numerator and our denominator by the denominator, if you think about it, in the problem you see on the screen right now, that would be multiplying by radical 2 over radical 2. And radical 2,
Sorry, I went back.
We're going to go radical 5 over
I want to
radical
do this
5.
one first. I don't know how I skipped a page.
So in this case, like if we're going to multiply by radical 5 over radical 5, well, anything divided by itself is 1. So radical 5 over radical 5 is 1. So all we are doing is multiplying 13 over radical 5 times 1, which does not change the number.
Exactly. However, by doing this, using specifically not just 1, but using square root of 5 over square root of 5, it will eliminate that square root of 5 in the denominator. So let's go ahead and do this example. You don't have a lot of room. You have some room in between the steps or below the word simplify if you want to work this out. Just find somewhere to work it out so that you know how to do it when it comes up in a problem. So to multiply the top and bottom by the denominator means you're going to get something that looks like this, where you are going to, on the top, have 13 times square root of 5. You need to remember that square root of 5 is not actually 5, so think order of operations. Exponents, or square roots, come first in the order of operations. So you're going to leave it as 13 times square root of 5 because you cannot solve that without a calculator. In the denominator, you get square root of 5 times square root of 5 because both of those are technically underneath that radical. You can multiply them and you get square root of 25. The second step is to now just simplify this. So looking in your numerator, right now there's nothing you can do to that without a calculator. The denominator, though, you have a perfect square. You now have the square root of 25, which we know is 5. If you could do more to this, like looking at inside numbers, meaning under the square root, and looking outside numbers, if anything can be reduced from top to bottom, you would do it at this point. But 13 over 5 does not reduce. Square root of 5 is not perfect. So this is actually the correct simplified answer. So this may be what you start with, but you need to make sure you go through the process and get this as your actual answer.
Now, take a couple of notes here. First of all, a radical is kind of like, if you look at operationally speaking, it's very much like a variable. So it almost looks like this, you could think of this as being 13x over 5. Well, if you had 13x over 5, you'd ask yourself, can I reduce 13 over 5? Or let's say it was 15x over 5. You know 15x over 5 is 15 divided by 5, which is 3, so it'd be 3x.
Right.
In this case, we don't have an x, it's a radical 5. So just keep in mind that between that 13 and that radical 5, there is a multiplication symbol.
Yes. And then again, similar to what she was just saying, and when I first did this, we talked about how we could not actually multiply the 13 and 5 because of our order of operations. The 5 on top and the 5 on bottom in our final answer, these cannot be reduced because this is not just 5, this is the square root of 5, which is actually a decimal. So that's, you have to, again, think order of operations, what comes first. This is actually the first step here. Because I said don't get your calculator out, this is as far as you're going to go with it.
Now, you need to think of it as like the reason we're not combining that radical 5 and that 5 is they're not like terms. And you're not going to put things that are the same, that are, if they're not the same, we're not going to put them together.
Right, exactly. So here's the example I first had up. This is just another example of if you want to do this one. I'd like you to at least have the last one. If you didn't get it, rewind the video. But same thing here. You have 40 over square root of 2. This is not reduced. You cannot reduce this because, as we were saying, you have to treat this almost like a variable. 40 would not reduce with square root of 2 because that's not really a 2. So we have to rationalize it. So we're going to multiply the top and bottom by the denominator. The denominator is square root of 2, so that's what we're multiplying both by. 40 times square root of 2 is 40 square root 2. On the bottom, we have 2 times 2, and we can do that because they're both square roots. The next step is to simplify. Well, now simplifying it, you get 40 square root of 2 over 2. That's where we stopped in the last problem, but as I was saying, you need to look and see if anything's reducible after that. Well, this 40 outside here, and this 2 is on outside. So would you be able to reduce 40 over 2? Yes, to 20, and then that square root of 2 just stays in the end.
Because this one did reduce and the last one did not, the 13 radical 5 over 5, I would highly recommend copying both these problems down so you have one example of one that will reduce and one example of one that doesn't.
So in your problems today, with our special right triangles, if at any time you are dividing by a radical, you have to do this. Otherwise, you will not get the correct answer. All right, so what is one of our, there are two special kind of right triangles. The first one we're going to look at is called a 45, 45, 90 triangle. The 45 and 45 and the 90 are referring to the angle measurements. So in a 45, 45, 90 triangle, you have two angles whose measures are 45 degrees and one angle with a 90 degrees. When you have this, because you have two congruent angles, this actually specifically becomes an isosceles triangle as well. So a 45, 45, 90 triangle is actually an isosceles right triangle. So therefore the two sides that are the legs are congruent to each other. The neat relationship, and I know you probably get sick of us hearing saying memorize, 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 but if you can remember these relationships, a lot of these problems become so quick and easy, it's like a piece of cake. The hypotenuse is always going to be square root of 2 times longer than whatever the leg length is.
Now the way I like to remember this one is, if you think about this, 45, 45, 90, you only have two different angle measures.
45 and 90.
That's it.
That's it.
So, and we know with both of our special right triangles, we're going to use a number that involves a radical.
Yep.
So, in your 45, 45, 90, you have two different angles, so we're going to use square root of 2.
All right, so at the bottom of this box, you have the sides are in the ratio of. It's going to be 1 to 1 for our two congruent legs, and then this is technically 1 square root of 2 because it's square root of 2 times longer than the leg. These three numbers are just going to basically be dilated. They're going to dilate up or down. One is going to be the smallest you're going to see, so they're going to dilate up from here. So a couple things. Looking here is your 45, 45, 90. Even though I don't have 45-degree angle numbers written here, you do know that these are congruent, so therefore they must be 45 degrees. So our legs, so the legs are congruent, so we're going to go ahead and put those right here. We know that again because these are 45-degree angles. This is just an isosceles triangle that you guys are used to seeing rotated around. So here's our vertex angle, our base angles. The hypotenuse would be our base. So therefore these are two congruent sides, and our hypotenuse is that square root of 2. So in the box here, we're just going to kind of, again, give you formulas. I think you guys are pretty good with formulas and just plugging stuff in. Your hypotenuse is always going to be found by taking whatever one of the legs is and multiplying it by square root of 2. And because I don't want you using a calculator, you're really just plugging in the leg in front of the square root of 2, and there's your answer.
Now, here's something I want you to think about. This is a right triangle, so you could solve for the hypotenuse by using the Pythagorean theorem.
Yes, you could.
And if you did that, you would find that the hypotenuse is equal to one of your legs times the radical 2. Because a squared plus b squared, in this case it would be a squared plus a squared, because both legs are the same, is equal to c squared. So if you solve that out, you find out, indeed, the hypotenuse.
You would have 2 times a squared. Well, what's the square root of a squared? A. Can you take the square root of 2? No. There you go.
Yep.
Yeah, perfect. Now, to undo this, again, think of this as an equation. If I wanted to solve for the leg, what would you do with the times square root of 2?
Well, of course, I'd have to divide.
So your leg is found by taking hypotenuse divided by whatever the hypotenuse is by square root of 2. And this is why we went over how to rationalize the denominator. You would not be able to leave your answer like this. You would have to start rationalizing it and go from there.
And again, if you were to use Pythagorean theorem and did a squared plus your leg squared plus your equals your hypotenuse squared, you'll find that this is your final solution.
Yes, you would get that. The only negative to doing the Pythagorean theorem, it's going to be more work.
And
Literally the only, so if you cannot remember this, you can definitely fall back on Pythagorean theorem.
And the other downside is the more math you do, the better chance you have of getting a number wrong.
Yep. So these relationships, not too difficult. Again, if you look at these, yes, these are two different formulas, but I'm just timesing by square root of 2 and dividing by square root of 2. So not too big.
So think about this. You have 2 L's, so 1, 1, and a radical 2. So you should be able to kind of use that to make maybe your own little rhythm, rhyme picture.
There you go. Rap.
Ooh.
Come up with a good rap for us on this. All right, so let's actually do some now on the back side of your notes. So here, again, it should be obvious that this is a 45, 45, 90 because you have 2 congruent complementary angles here. We're going to find x first. Well, we know x is one of our legs. And because this is a 45, 45, 90 triangle, you know that the legs are equal to each other. Well, one of them is given as 13. So I know that x is actually equal to 13.
That was like super easy.
Isn't it? Y is our hypotenuse. Well, if you look on the other side of notes, we wrote that the hypotenuse is equal to the leg times square root of 2. Well, what is our leg equal in this case? 13. So 13 times square root of 2 is actually your answer. So x is 13, y is 13 square root 2. Done.
Kind of liking these special right
Yeah.
triangles.
Next one, even though I did not write this angle, we know that the acute angles in a right triangle are complementary. The complement of 45 is 45. So this is another 45, 45 degree angle.
Don't get creeped out. You see a 6 radical 2. Trust me, not a big deal.
Not a big deal.
Solving for a is going to be super easy because you know the leg equals the leg. So you know a is equal to 6 radical 2. Easy.
B is going to be your hypotenuse. Well, you know that in a 45, 45, 90 triangle that it's going to be the leg times the square root of 2. Well, what is our leg length?
6 radical 2.
And then you're going to multiply it by square root of 2. So it's going to look like this. You're plugging in the leg, which is 6 root 2, and you're going to times it by square root of 2 because it's square root of 2 times bigger.
Now, keep this in mind. Again, between the 6 and the radical 2 is another multiplication sign.
Yep. Now, the numbers you can multiply are going to be the 2's because they are both under the square root of 2. or I'm sorry, they're both under the square root.
Think of it like this. Anytime you have something times by itself, x times x, it becomes,
X squared,
yeah. And what undoes a radical?
a square root, or a root.
Yeah, so
No, what undoes a radical?
what undoes the square root? It'd be squared. So if you do square root 2 times square root 2, it becomes square root 2 to the power of 2, which ends up being 2.
Right, because you're getting square root of 4, which is 6 times. And then don't forget, as we said right here in this step, this is actually 6 times square root of 2 times square root of 2. So when you deal with the square roots, it ends up being just 6 times 2, which gives you a hypotenuse length, or B is equal to 12. So I went baby steps here. I wrote every little step. Please do that here.
In your notes, just for practice.
In your notes, and then from there you guys can use the shortcuts and get to the final answer if you choose. All right, next. So this time 16 square root of 2 is going to be our hypotenuse. So our leg is always going to be equal to whatever the hypotenuse is divided by the square root of 2. Well, in this case, what is our hypotenuse? 16 square root of 2. So when you plug it in, it ends up being 16 square root of 2 divided by square root of 2.
But wait a minute, we have square root of 2 over square root of 2.
So do I need to rationalize the denominator here?
Well, I would say probably not, because radical 2 over radical 2, we've had this conversation earlier. Radical 2, anything divided by itself is just 1.
So A is just equal to 16, because the square roots of 2 can cancel out.
But let's think about this. If you remember, we said that the short leg could always be multiplied by radical 2 to get the hypotenuse.
Correct.
So
that's kind of the pattern shortcut we want you to see. If this is 16 square root of 2, then it must be leg square root of 2, so the leg therefore must be 16. And then to find B, well, B is just the other leg. We know that the legs equal to each other, so what's B equal to?
gotta be 16.
Gotta be 16. All right, and the last one on this page, I'm giving you the hypotenuse of 11. So to find x, we would do hypotenuse divided by square root of 2.
Not a big deal.
Well, in this case, if I were to take 11 and plug it in, you end up getting, not that, I clicked the wrong place, my bad. I'm being too high tech. Okay, you end up getting 11 over the square root of 2. Now in this particular problem, you cannot simplify 11 with square root of 2. So we are going to need to go through the process of rationalizing the denominator. If you remember, you multiply the top and bottom by the denominator, which is square root of 2. So 11 times square root of 2 is 11 square root of 2. The denominator is square root of 2 times square root of 2, which is square root of 4. Square root of 4 simplifies to 2. This is not reducible, so this is your answer, 11 square root of 2 all over 2. Y is going to just be the other leg. Well, legs equal each other, so therefore y must also equal 11 square root of 2 over 2.
So easy.
So that is going to be the process for your 45, 45, 90. I think I gave you the most difficult type. This is going to be the most difficult type right here. I think the rest should be pretty easy for you guys. So now we're going to look at our 30, 60, 90 triangles. 30, 60, 90 triangle is the only other special kind of right triangle you're going to look at. It's when you have two acute angles that are 30 and 60 degrees, which are complementary, and the other third angle is going to be your 90-degree angle. The relationship here, your hypotenuse is always 2 times the length of the shorter leg, and your longer leg is always going to be square root of 3 times the length of the shorter leg. So the way we remembered 45, 45, 90 was square root of 2 because you have 2 different angle measurements. Well, this one has 3 different angle measurements, so it must be the one with the square root of 3 in it.
Oh, that makes so much sense.
Yes. So that's how I always remember which one goes with which as well. So the ratio you're going to have is 1 to square root of 3 to 2. Now, why did I put the 3 in the middle? Isn't 3 the biggest?
Well, if you think about this, let's use the stuff we know to figure out the stuff we don't know.
Okay.
Okay, so I know that the square root of 1 is 1.
Correct.
Well, the next one I know would be square root of 4.
Yes.
And the square root of 4 is equal to
2.
2.
Oh.
So if the square root of 4 is equal to 2, doesn't that mean anything smaller than the square root of 4 would have to be smaller than 2?
So that's exactly right. So you need to think of this actually as square root of 1, square root of 3, square root of 4. That's why that goes here. So that's, remember, the hypotenuse is the longest longest side of a right triangle. 2 is the biggest. So that's why it's like that. So just remember it goes in that order. So with looking at this, your hypotenuse is going to be your hypotenuse. That should be a pretty easy thing to look at. Your short leg is always going to be opposite your smallest angle, which in this case is going to be that 30-degree angle. So short leg is going to be the magic one because it's the 1. So always find your short leg as quick as possible.
And it should be a no-brainer because we've already talked about how the hypotenuse, the longest side, is always across from the biggest angle. So now the fact that this little side or little leg is across from the little angle,
There you go.
that should make some sense.
All right, so for our formulas, your hypotenuse will be found by taking the short leg. How would you make 1, 2? It would be just the short leg times 2.
Well, that's simple.
Double it. And then to undo that, you would take the hypotenuse and
Divided by 2.
divide it by 2. Magic.
That one's super easy.
And then long leg, short leg is going to be very similar, but instead of using 2, we're going to use square root of 3. So to find your long leg, you would take your short leg and multiply it by the square root of 3.
Easy.
To find your short leg, if you know your long leg, you would take the long leg and divide it by the square root of 3.
Ooh, don't forget to rationalize your denominator.
Exactly. So there are your formulas for this. Again, I know it's 4 formulas, but really it's just 2. You're either doubling or dividing by 2, or multiplying by square root of 3, or dividing by square root of 3.
I want to try some problems.
Okay, we have 3 problems to do. So in this problem, you can see it's a 30, 60, 90 triangle. The side I am giving you is the side that's going to be easiest to know first. It's the short leg. And I know it's the short leg because it's opposite that 30-degree angle, which is the smallest angle.
It might even be helpful for you all to, on the 30, 60, 90 triangles, to write that ratio on, like we were writing O, H, and A, write your ratios on the 30, 60, 90. So down by
Like
26,
1,
you would write 1,
square root of 3.
and then B would be 2.
2.
So you know
That
how
can
to
be
get from
helpful.
one to the other.
So A is the long leg, or the square root of 3 side. So to calculate it, if you look back at the other side of your notes, it would be the short leg times square root of 3, because A is our long leg. So to find the long leg, we just plug in short leg and times it by square root of 3. Well, in this case, what is our short leg? It's this 26 down here. So it's going to be 26 times the square root of 3, or 26 root 3.
So easy.
B is our hypotenuse. Well, B we know is going to be the short leg times 2 then. Well, what is our short leg again?
26.
So it's going to be 26 times 2.
52.
So B is 52.
So easy.
Again, that's going to be the easiest because to find A and B, you're multiplying. Multiplying is always a little bit easier than dividing.
To be honest, with your 30, 60, 90 triangles, you truly are hoping that they always start off by giving you either the short leg or the hypotenuse. The difficult ones, which we will do as an example, is when they give you the long leg.
The long leg, which I think we're doing now. In this case, you can see that I'm giving you the long leg. How do I know it's the long leg? Because it's opposite the 60-degree angle. So I know the long, if I were to label my ratios, I know this would be 1 then, square root of 3, and 2. Well, to find D then, which is my short leg, I would have to take whatever the long leg is and divide it by the square root of 3. Well, I just said our long leg is 9. So I'm going to get 9 divided by square root of 3. Well,
Isn't that just 3?
if we didn't have the radical on the bottom, yes, it
Oh
would be.
my
But
gosh, I forgot.
remember that
Okay.
square root is there, so we can't just do that. So when you have this and it's not reducible, you
We have to rationalize the denominator.
So to rationalize our denominator, we multiply the top and bottom by the denominator. And you end up getting 9 square root of 3 over the square root of 9. Well, what is the square root of 9 on the bottom?
3.
And then you have one more step here because of these outside numbers, 9 over 3. Again, as we said early on, if this was just 9x over 3, we would reduce the 9 over 3 to,
3 square
and
root
then that
3.
square root of 3 is just going to be there.
Excellent. That wasn't as bad as I thought it was going to be.
No, not too bad.
Wait, we have the short leg now.
We know our short leg is 3 square root 3. So to find our hypotenuse, remember our hypotenuse is going to be the short leg times 2. Well, I just found our short leg is 3 square root 3, so I'm going to plug 3 square root 3 in.
Now be careful. You're multiplying 3 radical 3 times 2. Or, again, this would be 3 times radical 3 times 2. If you remember with multiplication, order doesn't matter.
Correct.
So let's go ahead and multiply 3 times 2.
So we're looking at just the outside numbers because this 3 here is the only one inside, so it's just going to be left alone. So 3 times 2 is 6. So our hypotenuse is 6 square root 3. Done. Last problem. This time I'm giving you the hypotenuse. I know it's the hypotenuse because it's opposite the 90-degree angle. You do not want to find y first because that's our long leg. And remember, or maybe you don't remember, but if you look back at your 30, 60, 90-degree page, all the formulas we talked about all had one thing in common. They had the short leg in common. Every single one of them talked about the short leg. So you always want to find your short leg as quick as possible. So we're going to find x first. X is our short leg because it's opposite that 30 degrees.
But wait a minute. Isn't the short leg just half of the hypotenuse?
So to find the short leg given the hypotenuse, you are going to do hypotenuse divided by 2, and in this case the hypotenuse is 16. So 16 divided by 2 is very easily solved. You get 8. And once again, just like the last problem, you know the short leg now. So now when we move to y, I know the long leg is the short leg times square root of 3. Well, what did I just find my short leg is? 8. So I'm going to plug 8 in, and I get 8 square root 3 for my answer. And that is how you do 30, 60, 90 triangles. Yay!
Yay!
So you guys should be able to determine your side lengths given one side and the fact that you have special right triangles. On all of these, let me be clear. You could use trigonometry as well to find missing side lengths. The issue I have with that is you are not going to get the exact answer, and I want to be clear, I am looking for exact answers on these, so you do need to use the special right relationships and the ratios to determine your answers. When you're given a test, these are going to be exact answers. So if you are using trigonometry, you're not going to see those square roots of 2 and 3 as part of your answer. If you have any difficulty, please go ahead and reach out to us at any time, and we will or won't answer you back.
Yeah, we'll answer you back. So, hey, Mrs. Weichel,
Hey, what, Mrs. Nats?
what's the best formula to get from point A to point B?
I don't know what.
Well, you just take an XY plane or a rhombus.
Ah,
Get it?
A
Rhombus.
That sounds like a fun trip.
Yeah, I'm not sure for who.
All right, thank you guys. We will see you in the next